Welcome, everybody. Welcome to the final presentation of the day. My name is Remko de Jong, and that guy over there in the corner is Martijn Blankestijn. We're going to talk a little bit about functional state today, or in this case, never-changing state and still getting things done. So, why this talk? Actually, this is something we encountered in a real project we did. We've both been programming in Scala for quite some time now. And once you make the transition into Scala, sooner or later you run into something called functional programming, and then you try to start doing stuff in an immutable way. So in one of my previous projects, we actually had a use case where we had to design or implement an algorithm for machine planning. And first we tried to do that in a mutable way, and it just didn't feel that right. There were some quirks with it. And then we tried to solve it in a more immutable way. And actually, what we ended up with was quite nice. And then we decided, why not share this with more people? So, the roadmap for today. First, we're going to have a simple domain to guide you through all the code examples. We will start with a traditional object-oriented approach that I'm assuming you're all familiar with. Then we will make a transition into a more immutable approach. And at the end, we will have devised our own functional data structure to handle state changes. So, warning, there will be code, lots of code. And the code examples will be in Scala. Don't run away yet, because we've tried to use, it's basically simple Scala. So the code examples won't have any of the advanced language constructs in them. So it should be very easy to follow if you at least have some familiarity with Java 8 and Lambda syntax functions, mainly. But for those that aren't too familiar with Scala, can I get a show of hands who has done something in Scala or ever seen Scala code? Oh, okay, surprisingly many. It was also quite interesting to see that apparently 2 presentations in the big room are about Scala, so not sure if it's gaining some momentum here. For all you guys that haven't done Scala, a quick crash course. So on the left, we have our simple Java structures. Is this readable, by the way? Okay, who cannot read this? If you cannot read this, please feel free to move forward and closer. There are seats here, so then that would probably help. Anyhow, at the top we can see a normal variable, a mutable variable. So we have a Scala equivalent for that. It's simply called var for variable. We have the familiar immutable variant. We prefix it with final. In Scala, we call that a val, stands for value, quite simple as well. And finally, we have some lambda syntax. As you can see on the left, Java requires a little bit more boilerplate, also sometimes referred to as the bun problem. You don't have that in Scala. You can just get a data structure such as a list, and you can call a map on it. Most noteworthy is the representation of the arrow, where Java uses a hyphen or a dash, and Scala uses the equal, so like the fat arrow, sometimes called. So then we have another construct. It's called a case class, which we use a lot. You could basically view this as the Scala equivalent of a Java value object. So you get some methods for free. It's completely immutable. And most interesting is the copy method you get, which helps you to get a copy of that class. So this should be easy enough. So I would like to give the word to Martijn, who will tell something about the domain.
Yes, thank you. The domain is easy today. It's not about beer. It's about a candy dispenser. And it has just two inputs. You can insert a coin, and after that you can turn and you get back a candy. And you can think as the candy dispenser as just as a big list of candies. And if you turn, you will get the first one that will be removed. Well, some very easy code. We have just one type of coin. It's just like a festival. And we have a case class candy that has a color, and color is in this sense just see it as a Java enumeration, blue, red, green. So then, quick show of hands who has, well, first I think who knows this book and who has read it and who came to the end at page 1200. No, not even me. It's a great book in which the concepts of object orientation are being declared. And Bertrand Meyer is also the proponent of the command and query segregation, stating that the class has basically two types of methods: commands that modify the state of the object, and queries that give information about the state of the object, but doesn't modify it. It has no side effects. If we look at our first attempt for the object-oriented code, we see a couple of constructs that need some explanation. In Scala, the default access modifier is public. That is for members, but also for classes. So we have a class machine that takes a mutable buffer, comparable to a list in Java, of candies. And it has a mutable variable coins. And because these are class parameters, they are also members of that class. So we can use them in the body. And well, we have the two basic operations. You can insert a coin that takes a coin. Scala has a different way of declaring functions. You have the def keyword, the name, the parameters, and then colon, return type. Insert coin does basically what you expect from it. It adds a coin to the number of coins that are inside the machine. And turn does two things. It mutates in place the collection we have by removing the first element and instantly returning that to the caller. And we have a getCoins method that exposes the coins variable. Because it's object-oriented, we keep our members private, and otherwise you could change the number of coins from the outside. And that's not good. Well, if we take it for a spin, we create a mutable array buffer with a couple of candies. Please remember the order. It's not the usual one. We have questions later. You're going to create the machine with the list of candies and the number of coins. And we take it for a spin. Well, code is as expected. You insert a coin. You have no return value. That's one thing I didn't mention here. It returns unit. That's basically Java void. So it doesn't return anything. And we turn, getting us a candy, and we can do an assert. This is Scala test code, but you can already see the equivalent in JUnit. But there are some problems with this, and there are also now some solutions. Well, it is about functional state. So functional programming is one of the alternatives that is already very old. It's from before structured programming, but it hasn't been feasible due to hardware constraints until a couple of years ago. And what are the problems? Well, part of it is with all that mutable state, sharing is no fun. We learned that at kindergarten. And if you go to concurrent programs, if you have mutable state, that's nasty if state is being shared. And the other thing, it makes your head hurt. And I say, oh well, why? I'm looking at code. It's perfectly understandable to me, but you're mutating in place. Why should that make my head hurt? Well, we are accustomed to that. There are a couple of problems with it. For example, take this simple function. Function called f. It takes an integer, returns an integer. And if we call that with 2, the result will be 3. Well, the hyphens aren't Scala, by the way. If we call that again, it's going to give us 3. Nothing out of the ordinary. If we call function 2, we get 3. If we pass that in again, we get 4. Then we're realizing, I've read Uncle Bob's Martin's book. This method should be called add 1, because that's basically what it is doing. But it's easy to follow. Even this one, it's getting complexer, but well, we are still adding 1, so we can even replace the inner functions with their value. So this is easy. But what if we look at it at another way? This is a different implementation of that function. It mutates some state that is wider available, that has a scope that is broader than the function itself. This function has side effects, as they call it. If you call it the first time, you put in a 2, you get a 3. Okay. You put in an F, or you put in a 2, you get 3. No, you get 5, because there was state somewhere else that has a relation to my current value. And if I nest it like I did it before, then I must go, okay, I have a 5. No, I have a 2. I put that in F. It was 5, so that's 7. And now I give 7, so I get back 14. And I don't going to even start to calculate this one. So it can be, even with this, a function simple as this, it can be quite complicated. So what are the ways that we can improve this for our candy dispenser example that has methods that change its state?
So let's try to take a more functional approach to this. So when you start with something, with a thing called functional programming, or you look it up, at some point you're bound to stumble upon this little term called something called referential transparency. Then you look at the definition. It says it's an expression that is referentially transparent if it can be replaced with its corresponding value without changing the program behavior. So if we looked at the last function, Martijn showed that this was clearly not the case. However, if you looked at the function before, the simple +1 function, that's an example of a referentially transparent function. It's also sometimes called a pure function. So why would you want to use this? So you get a few benefits. First of all, referentially transparent code is easier to reason about. I hope the previous example showed that even with simple cases, mutable state can already become quite hard just with simple functions and simple changings of state. Then it's very testable, because basically what you're doing, it's just a function. It's data in, data out. Nothing happens. You can call it once, you can call it twice, you can call it 1,000,000 times. It will always produce the same output given the same input. And the nice thing about functions, and these pure functions, is also that you can compose them, which basically means you can take a bunch of functions, can do some magic, combine them, and you can build other functions that do even cooler stuff, more powerful stuff. And besides this, all this immutability also makes your code better to parallelize, because there is no shared state, so you can freely hand out copies to other processes and start running computations on those. So what if we're going to apply this to our domain, the candy dispenser example? So remember the mutable variant. So first of all, the thing to note here is that basically our state is quite implicit. And the state of the machine is basically captured in those variables, those private variables, the mutable buffer and the variable that holds the coins. So it turns out there's actually quite an easy recipe for making mutable code more immutable. So what you do is you start making stuff explicit. So we had state. So what we do now is we make that explicit. So when we call the method, so for example turn, we pass in the input state. In this case, the machine, the old machine. Then we do some magic, and we produce as output not only the candy, but also the new state of the machine. So you can see the types of the machine, both the same type, but one is referring to the old state, one instance is the old state, and the return value is representing the new state of the machine. Here you can also see that we're using the copy method. That is something that we get for free by using something called the case class. And this should be fairly simple thing to do. It's almost a mechanical refactoring you can apply. So if we take this for a spin, we again have the candies. We create the machine with the candies in order, the blue, the red, and the green one, 0 coins. We insert a coin, we turn the handle, we insert another coin, we turn the handle again, and we would expect the number of coins to be 2, and we expect the number of candies left to be 1. So far, so good. Right? So, did anybody spot the bug in this code? Exactly. I'm not sure if you can see it, but the final state in the second calling of the turn method should be red now. We're actually passing M1 twice. And that's obviously a bug because we probably meant to pass the second state as input instead of the first again. Or sorry, in this case, the third state. Excuse me. So that's quite problematic because your compiler cannot help you here. These input states and output states are the same type. So the compiler will flag this as okay. So you will need to rely on unit tests in order to capture these bugs. And this is a fairly simple example, but you can imagine if you have to do all this manual wiring, that it can get quite complex pretty fast. So if we try to sum up the pros and cons of this approach, what we see is basically it's simple, right? The only thing we did is we made the state explicit. We did have to add some extra arguments and extra return value. So there's more boilerplate that we're passing around. It is immutable, given the fact that we want our stuff to be immutable, given the reasons we've shown you before. Yeah, the downside, it is still quite error-prone, and with all that state you have to keep track of yourself. That's not a really fun thing to do. So, is there something we can do about this?
And we wouldn't be standing here if that was not the case. So, if you take a look at the type signature, well, we have the def, we have the turn, it's just a name. It takes a machine and it returns a tuple of a machine and a candy. We can also look at it more abstractly, like a function. Its input is a machine and it returns a tuple of a machine and candy. Or even more abstract. Let's just have any type, call it S, that will be the state. And a function that takes one and returns a new state and a value, which we call A in this case. But that could be any type. And to remember, so this is not valid Scala anymore. It's always from an initial state to a new state. Then we're going to make a leap. We're going to set up for where we are going now. We're going to wrap that function into a case class. So we have a case class, state, with 2 type parameters. A type that will stand for the state, and one for the value. And that function will be the function we just saw, state to a state value tuple. And there will be a method on that case class, run, in which the actual method is applied. And in this case, we are ripping apart the definition. the description what should be done, the function, and the execution of it, the computation that when that is going to be done. Because the method run will take an initial state, and it will apply that function, thereby returning a tuple of the new state and the value. Well, that's all kind of abstract, but how would we use this? This is our old example with the turn method we're going to look at first. The turn basically has the input and the tuple of state and value as output. So we can just replace it with that state. The state machine candy wraps that function of machine to a new machine and candy. And what would be the implementation? And this is what Eric Meyer says means by following the types. Well, we are going to return a state, a new wrapper around that function. How does that function have to look like? Well, it looks like it did before. And so we're not, the old method is returning a changed object. This is just returning a wrapper around a function. It is not doing anything. Important distinction. But what about inserting a coin? That doesn't even look like the function of a state to a state value. Well, we can twist it a bit. We can say, well, insert coin doesn't return a value. And as I said in the first part, that's basically saying it returns unit. So it returns a tuple of machine and unit as its output. And we can make use of currying. And that basically says if you have multiple arguments, you can translate that into a sequence of functions with a single argument. You can do that in Scala. So you can say, well, first have to make it type correct, so it will return unit. But there's a subtle change. And now we have two parameter lists. The code is still valid, but now we could return that function. And we can change it into insert coin. That takes a coin, and it returns a state. And this is exactly the same, because state needs a machine, and it will return a machine to unit tuple. Implementation, well, it's a state. So we're going to create a new state. What's the function? Well, we already know that, because we have defined it before. Also in this case, the difference between the first and the second is we now returning a function, a definition. We're not doing anything. And that we will see when we look at how are we going to run this? How are we going to run this program? Well, first, you can say machine insert coin. We made the definition a part of the object. But we call the function insert coin that returns state. That only wraps that function. Then we have a new machine, and then we can call run on it. And then that's the part when the computation is being done. And we get a result, in this case, a new machine and a candy. And, well, the candy should be blue. That was the first one. But did we make it simpler? Or did we make it more complex? Well, if this was the only thing, we would make it more complex than necessary. But there are some very nice things we can do now with this state structure to make our program easier and easier to program with. And that's by composing functions.
Exactly. Let's look at how creating all this boilerplate, extra complexity will actually help us. Of course, you're probably all familiar with the term that adding another layer of indirection is the key to solving every problem. So let's apply that here as well, I guess. So composing functions, what's it all about? Basically, you take simple individual components, you mix them together, and you get something more powerful. So let's start simple. Let's look at map. Assuming everybody here is familiar with map, basically you have a collection, map function. It takes another function which describes what to do with every element in that collection. So we're pretty familiar with using map on a list, but it turns out that lists are not the only structures on which you can use map. We could also introduce it on our own data type state. So what does it look like? Again, map, it takes a function. We call it transform here. You can give it a value, in this case of type A, and it will transform that value into something of type B. And what it returns is a state, and remember, state is nothing more than a wrapper around a function. So in reality, it just returns a function. And in this case, a function that, given an old state, returns a tuple of a new state and a value of type B. So let's try to implement this. So we start with the return type. We need to return a state. So let's create one. And in this case, our state will need to return a value of type B. This will be the main difference. So again, state, just a wrapper around the function. We need to give it that new function. So the function always starts with some input state. In this case, we chose the name S0. You can give this any name you'd like. What then? And this is actually a very, very nice thing about functional programming, that if you have a method definition, something like map, for instance, sometimes you see that the implementation more or less unfolds automatically. There aren't too many ways you could implement this function. Because if we look at this piece of code and we have some input state, what can we do with it? Well, if you look carefully, we see that we're inside a state class, which means that we have access to function f, which actually takes an input state of type s, which is exactly what we've created with that s0. So we can use that. And we can call run with s0. And it will return us a tuple of a new state, let's call it s1, and a value of type A we chose to call A. The only thing left now to do is to make sure we return a B instead of an A. So next step, we return a tuple of S1. And hey, we happen to have a function lying around, transform, that given an A returns a B. And there it is. We have map. And as you can see, it more or less naturally unfolded. So if we look at this schematically, you could view this entire block as the new function that is returned. So what we do with map is we have our initial function, and we transform that function into another function that does something different. And we do that by combining two functions. In this case, function f and function transform. And if you look at a function as a whole, you can still see as an input, it takes an S0 of type S, and it returns a new state also of type S, S1, together with a B. Simple, right? So let's take this for a spin. First, we call machine.turn, and this doesn't do anything yet, as Martijn explained. This just returns a function, in this case, wrapped in a state class. Then we can define our program. So we take that turn function, that state, we map it, and in this case, we are not interested in the candy, but we're only interested in the color. Then we can actually run it. This is actually where the execution happens. And it returns the color, not the candy, but the color, because of how we used map. Or if you do it a little bit more idiomatically, in Scala, the compiler is quite strong, so it can infer lots of types for you. So you could choose to omit some information. The compiler is smart enough to figure that stuff out on behalf of you. So it turns out that these patterns, these things we do, are not that rare. So there are actually there's a name for these kind of functions, and those are called combinators. So there's a really nice formal definition of a combinator. It's a higher order function that uses only function application and earlier defined combinators to define a result from its argument. Or, like I said, you just have a function that takes a bunch of other functions, does some magic, combines them, and voila, you have a new function. So next thing could come in handy is if we try to sequence state functions. You can imagine we have a machine. It's nice that we can insert a coin, turn a handle. Probably we want to do that more than once. So we could go ahead and try to use map to see if we can combine with functions to see if we can chain different state functions. So does anybody care to guess the type signature, the return value, if we have that insert function and we map it with a turn function? You can see state gets nested. So now we have a state of a state. That's not what we want. What we want is, if we chain state functions, we want to get just a state and not a state of a state. If we had to apply, suppose we had a sequence of 10 function calls, then we would have a state of a state of a state of a state of a state. That doesn't make for really nice programming. It gets quite complex pretty fast. So it turns out there's another combinator called Flatmap. Of course, also familiar from list. Almost the same as map. Main difference is the function we pass to Flatmap. Given a value, it actually returns a new state. Or in this case, a state wrapped around the function. So given a value, it returns a new function. So let's try to implement this as well. Again, we want to return a new state. So let's create that. And we can see that the beginnings are almost exactly similar to map. Again, we need to produce a new function. It starts with an S0. Can we put that somewhere? Yes, we have a function that takes an S0. It's called the f. We run it. We have a new state. We get our value a. And now we can use a, because that function g takes an a and returns as a new state. So we pass a to g, and it returns a state. We're not quite there yet, because now what we actually return is a state of a function of an S0 that returns a new state. But as you can see here, we're building the new state object, and it needs to have a function from an S0 to just a tuple. So we're not interested in returning a whole state, but just a tuple in this case, because we're building up that new state. But fortunately, the state object, in this case the new state object, also has a run function, and we can pass it the intermediate state, and we have our new state. Schematically, it shows very, very nicely that you can use this to chain the functions together. Again, you see we have two functions, f and g, both wrapped in a class, but this is just to be able to compose them. It's not JavaScript where functions can have other functions defined. It's still Scala, so we need to wrap it in something in order to create those combinator functions. But you can see we're combining f and g to create a whole new function. So if we take this for a spin, we can now compose our insert coin function together with the turn function. And if we run that program, it should return the candy. However, suppose we want to do more steps. This quickly gets a little bit cumbersome because I insert my coin, I turn, insert another coin, turn again. Anybody that's still been paying attention, any idea what the return value is? Yes, it's a red candy. All these really indented code kind of looks like callback hell. This, not really my thing. But that's the beautiful thing about Scala, that if you have a Flatmap defined, I'm simplifying a little bit, but it allows you to rewrite this using something called a for comprehension. Not to be confused with regular for loops in Java. These are a completely different beast. But as you can see, this should be a lot more readable than the previous slide. It does exactly the same thing. It's just syntactic sugar, so you can understand it a little bit better. So it almost looks like imperative code, right? So I have a program. What do? I insert a coin. I turn, insert a coin. I turn again, and I return the final candy. Easy enough. So can we make this even more imperative?
Well, of course, it's a bit of a saying from the past. Yes, we can, as he will be out of office soon. But if you look at this program, the arrow is pointing towards where the result will go. And the underscore is basically saying, well, we're not using that value at this moment. We're not interested. We are not even giving it a name. So we can't reference it, but, well, we don't want to. Only in the last one, you have the turn, and then you get back the candy. And that will eventually, the program will be a state of a machine and a candy. And so we're basically wiring functions together. We're having functions and combining them into new functions in greater, we're basically creating compositions. And somewhere in that, that looks rather imperative, and that's nice because it's also easy to follow. But what if somewhere in that for comprehension, in that path of all functions that we bind together, what if we want to do something with the state itself? If you look at this slide, well, the only thing we can get our hands on is the candy itself, the value. The state is being wired through. Well, to make it more imperative, we would like either getters and setters back. So what if we wanted to do something with the state? Well, you can define a get function that will return a state. Only that function will return both types of the state that are equal. So we're getting a state that wraps a function that takes a state, and we are returning, well, basically a tuple of both. So that way, if you want to do something with that state in your for comprehension, this is the way to get it out. Well, if we have the getter, we should also get the setter. What if you do not want to do anything with the value, but you just want to change the underlying state? How can you do that? Well, of of course, with the returned function state that we're giving the new state that it should replace. Well, that looks like this. We again create a state. Well, we're not interested in the argument that function is getting because we are replacing it. So here again, the underscore saying I'm not interested. And the thing that I'm returning is, again, a tuple of a new state in unit. And this way I can replace the state and still do not leave the scope of all the functions that are wired, where the state is wired through. And then we come to the refactoring, and then is this so much better? Well, I'm not even going to ask for a show of hands because I think I know the answer. No, this is not better. This is more of a way of showing how it could be done. Yeah, so insert coin could be implemented that it returns a state of a machine and unit. The state get is a function that delivers the machine, and the state set would basically be the new state would be the one with the added coin, and we would return that one. But this is not nice. But there's another easy addition to the state we can make to make that more easy. We call it modify. You can modify the underlying state. And how would you modify it? Well, you just give it a function that takes the old state and makes a change to that state and returns that. And the implementation is, again, if you follow the types, it is something to get used to, I must honestly say, but then it is easier to follow the type. And then you're returning a new state. It gets the parameter state, and we're applying that function and returning unit as the value. And then we could write it like a one-liner that much better shows what it is going to do when it is invoked. And there's more. We're not going to go through all of them. But there are a lot of functions that can help you create and manage state manipulation by separating the definition of the changes you want to make and then running them in one where all your functions will be fused to an end result. So looking at what we have created now, the pros, it's simple. I will get back to that one. In the way it uses the Scala type system. We're not using implicits or type level programming or other kind of advanced Scala stuff. We still have that everything is immutable. What we've gained is the automatic state wiring. We're basically composing functions. And you do not see the state being wired through by using a state data type that abstracts that away from us. And we even got back a part of the imperative way of using it by using for comprehension. That's eventually still syntactic sugar for the flat maps. On the other hand, is it simple, really? I would argue yes, it is, but it takes some time to get used to. The thing with the types, the functions you pass around. I think we're in a much better shape coming from Java with Java 8 and functions than we were before. We can do a lot already in Java 8. But if it comes to functional programming, Scala still makes it easier, but the whole model you have to get used to. And there is a performance impact. You're chaining all those functions, you are not mutating in place, so you're using more memory. That's true. It depends on what kind of application you're writing. my argument would be if you're going to a database once or doing a remote call once, well, that performance impact doesn't matter. But for some applications, it will. And so that's basically the overview of the pros and cons of using the state data type with respect to the immutable variant and the object-oriented variant. And this brings us to the end of the presentation. The presentation is available on this URL. There's some other interesting references, especially functional programming in Scala. It's a big red book. If you want to know more about functional programming in Scala, just buy it. And a couple of talks. And I don't know, we have time for some questions. So if there are any, this would be the time. Or you're all waiting to get beers. Ah, I see one there.
Well, I'm feeling that you're making the thing really overly complex. And I was thinking about, well, you can also make it more simple and more object-oriented way by just having a kind of state object and then remember what are the transitions during the time.
Maybe I can try to answer that one. So your question is, it seems overly complex what we're doing, right? Yeah. Okay. What we've shown you today is part of the picture, because the functions we use can be even more general, which means that you can also combine this structure, this state structure, with other structures. So you can compose it with other functions and build even more powerful features. Was a bit too much to include that in this talk as well. But yeah, if you just view it on its own, and I also agree with Martijn, it also does take some time to get used to. Part of it is also it is more complex, but that's also what you pay if you want to be immutable. And you need to do some work. You need to make some stuff more explicit, and yeah, that requires some indirection. And yeah, the problem with indirection is, though it solves every problem, is that it also adds more complexity. But if you were looking at it in just this really tiny use case, so of course we just used a very simple candy machine. You might as well argue that, yeah, if it's this domain and it's not going to change, just make it as simple as possible, or just do it in a mutable way. And it's also not that we're advocating that doing stuff in a mutable way is bad or something. It's just that nowadays there are also other viable approaches. And it is very interesting to take a look at those. And of course, in the end, depending on your particular use case, you will need to make that decision. That's always that's the consultancy answer you're getting. Depends. Does that answer your question?
Looking at the time, I think there was an option that there was they are going to show a small. Yes, they are going to show the after movie.
Please stay seated.
So we'll be silent and we'll be here for questions. But I think now the floor is not ours anymore.
Yeah, and thanks everybody, of course.
Yes, thank you.